Gilbert. Formerly from Simon Fraser University. I finished my PhD in applied mathematics and I'm looking for a job. I have experience in biophysics and image processing, basically PDEs, solving PDEs, asymptotic analysis, numerical solutions, and so on. Thank you, Amir, for inviting me. Today, we will be talking about flexible neural representation for physics prediction. And this paper has been written by Morocco and the rest. Most of them are from Stanford. Only one is from MIT, so Joshua. And let's go here. So if you look at the picture, here you have a simulation of a cube, a box, and it's jumping down, falling down onto the ground and bouncing off the ground. And this is a simple situation. We as humans can have some intuition. We can predict the physics in the world. We can predict this simple situation and much more complex situations. We can give a reasonable prediction of what's going to happen from our experience about the environment, the physics, the objects, interactions in the environment. So in this paper, we are trying to capture this physics, so translations of objects, rotations, deformations for soft objects, collisions between objects, also object permanence. I mean, the object should be still be there after the prediction. We want to do it at multiple scales, and also we want to include occlusion. So as I said, humans are good, reasonably good at prediction, and they do it at multiple scales. I mean, sometimes you need to look carefully at some parts, and sometimes you can do the general thing, how the object is moving, maybe like an intuition of the center of mass of the object. And sometimes you need to figure out how the collision will happen. At least it's thought that we're good in physics at some level, and we learn about object permanence, occlusion. We can figure out the occlusion and deformability of the objects. So replicating these capabilities in machines should be useful for many applications, like, for example, reinforcement learning, robotics, and so on. We want to know the physics, what's happening in the environment. Relying on images alone, videos, is not easy. Without including some prior knowledge, it's not easy. And there are some physics engines, mathematical tools that are used for prediction with various successes and limitations. But these tools are hardwired. They don't learn. So you keep the parameters of your environment, and it's a fixed environment, and you run it, and you see what happens. And you need a lot of resources, of course, and at least in the mathematical side of things. So in this paper, they propose a neural network, which is differentiable, can learn. You don't need to preset the parameters of your environment. So, since I'm a mathematician, I'll just one slide about mathematics. So, I mean, if you have an object like this, it can be a varying complexity, a solid object, and you want to see how it behaves under varying forces in the environment. There is some varying properties like stiffness, also liquids, gases. I mean, these are only some examples. There are some equations. I mean, a lot of work in mathematics, physics. They have a lot of equations that depending on your case you can use, and you can solve these systems. So you need the boundary condition, what's happening around you, and the properties inside. You have some equations according to your physical situation. You can use them and solve. But they require a lot of resources. It's not easy, and it's for a specific problem. You need to define it very well, and it takes a lot of time, resources. You have the physics simulation software like Flex, Unity 3D, and so on. Flex is part of Unity 3D to predict what happens in the environment in a realistic fashion. Not necessarily very accurate, but realistic for a human eye. Plausible, I mean, situation of what could happen.
Quick question, if
Yeah.
I may. So the FAE, when you say slow and consume a lot of resources, you're talking about FAE or?
I mean, finite elements and numerical methods in general. Yeah. Okay, in this paper, they assume everything is made up of points, particles. These particles have a mass, have relations in between, and they interact with each other with the environment through gravity, for example, or through collision with each other, or with different surfaces in the environment. And these are actually the objects they used in their simulations and test experiments. I think this is the, no, it has the slide, sorry. Okay, so I mean, if we talk about solid mechanics or fluid mechanics, we have forces, external forces at the surface, body forces like gravity. You may have some forces that, I mean, if the environment, you don't know much about the environment, some forces you can't really specify. In this paper, they're talking about effects. They don't talk about forces. So one particle affects the other particle. How it affects it, it's some internal representation to the best of my, what I comprehended from the paper. So it's some internal representation which summarizes these things.
So, like the internal forces is what holds the object together?
Yeah, so here, I mean, each particle is, holding each other, or, I mean, if one particle moves, if it's, I mean, nothing is entirely rigid, but if something moves, it can pull on the other particles. So these are internal interactions between the particles.
And there's like is it like a network where it all just affect the adjacent particles, or is it like a kind of like a radiant function that gets weaker over distance? So basically,
it's
how do you
not
transfer
specified.
So
it's not specified exactly, but I'll show you. So they do something which is computationally efficient, but they don't specify what exactly should be. I mean, it's not necessarily that you're affecting only your neighbors, or you're decaying with distance.
But isn't like one of the parameters, isn't it like how strong the bond is? Like if I have a solid object and I throw it on the ground and expect it to behave differently than, let's say I have
the stiffness.
Yeah, stiffness.
Yeah, stiffness, how strong is the bond between two, the interaction between two particles.
And this interaction is always like
so it's adjacent, yeah, no, but there is interaction also. Basically it's adjacent, but there is also interaction between centers of masses. But as you said, it's adjacent. Actually, sorry, they don't specify adjacent. This confused me, but they don't in the paper. They don't specify it should be adjacent. There are relations between all particles. Maybe I missed something, but
Chris, what is, you can say it loud so that
if you have
everyone
something.
hears.
Oh, yeah, no,
It's a slide.
it's literally that thing right there. Yeah, I'll probably break it apart.
Okay, if you have an object in your environment or surface, you divide it into particles, as we said. They said 50 to 300 particles per object. And for surfaces, they put thousands of particles, 5,000 particles. These particles, you don't want to deal with all these particles and all their interactions together. It's computationally expensive. And so you do a graph hierarchy. So you do something like a center of mass. So you take, for example, these 8 particles and you take the center of mass. This constitutes an intermediate node that summarizes how these particles interact with these particles, for example. So you do it in a recursive fashion. I think they have eight clusters at each level. So you take the leaves or the original set of particles, divide them into maybe 8 clusters using k-means, and then these 8 clusters they're connected to some node, and these nodes also for each of these clusters you can subdivide further and further, maintaining that you have always 8. You want to reach that you have 8 leaves always at the end. So here, for example, this is only two levels, 3. So you have this 8 summarized with this node here, for example. Let's take the reds. Each particle has a position, velocity, and mass. Okay, and this particle has the center of mass, average velocity, and cumulative mass.
I think you also mentioned something like material.
Mm-hmm.
Is there a material dimension as well?
Mass.
Material. So what kind of material?
There's interaction
Okay.
between particles, the stiffness, or Rij.
Oh,
I don't understand what's happening from like the 3rd one to the 4th one,
yeah.
where you have 8 circles, like 8 spheres, and then it becomes 1 sphere.
No. These are all the particles
Yeah.
of the object. Originally, you have the object. You have
Right.
300 particles.
Sure.
You divide them into 8 clusters, for example. 8, whatever you specify. Okay.
But the fourth step on the illustration, why is it meshed together? What is that? What is he trying to say?
I think it's some kind of...
These are the particles. You divide them into 8 clusters. Okay. So 1 cluster per second and so on. You devise a new node in your graph. So originally you don't have all this. Originally you have only these particles. These particles. Okay. You divide them into.
The illustration right before that.
Illustration.
Or in the
No,
high,
like
or in
the
That's the center of
round,
mass
the
of
one
the
circle.
I didn't understand.
The
So
sphere?
this is the
The
sphere.
sphere? And,
This?
yeah.
Yeah.
So that's where you get the center
What is
of
that?
mass? or-
Yeah, just wondering, this is called like an octree. So in like computational geometry, this is a very common data structure. So you kind of like, kind of divide your 3D space into like 2 parts on each like direction. So you get like, you get the first division, and then you kind of like concentrate everything into the center of mass to get the second thing. And the third one is basically the entire mass of object positioned as at the center of mass of the entire object. So that's basically different levels of detail of the same thing.
It's just,
Okay.
if you want to do it correct, you have to calculate like how do all particles or all atoms interact with each other. And just to avoid the computational overhead of just useless calculations, you just group your object up and then do a hierarchical clustering, right? Just do it on the lowest level, and then you get your first layer of clusters, and then you calculate how do all the points in this cluster influence each other, and then you go to the next level. And the top level is like the center of the object, and then the center of the mass of the whole object.
So when you say cluster,
Right.
what? Oh.
I think it's regular, just you regularly subdivide your mesh. I think so. Aren't you? Or
Yeah, it's regular, but when,
So
because there's like multifold methods as well. And like,
So they don't specify, for example, the distance, or as you said, quadrants. They don't specify this. They just divide them, I think, as they come. Yeah, but yeah, here it seems like a regular nice thing where they divide them. But I didn't sense that they have like this regularity in dividing. So they have all these leaves of one object. So all these leaves or all these particles are for one object, right? Now you start dividing them into subgroups, and these groups you can further subdivide them into further subgroups until you reach further details in each subdivision.
Sure. Could you? Okay. So I have two questions. They're clarification questions. So one, when you say clustering, what type of data point we're dealing with? So is it
So you have the position, velocity, mass.
position, velocity, and mass? And so you've given that.
So this is the regularity you were talking about. Yeah. So you use k-means on this. So these are your coordinates.
Okay, those are your raw inputs: position, velocity, and mass. Okay. And the second one is, I'm not sure if I understood. So from you have like 1, 2, 3, 4, 5 objects over there. The transition from the third one to the fourth one, what's it trying to say?
It's from 3 to 1.
It's
So,
all the same object.
I mean, these. What's the center of mass?
Oh, it's all the same.
It's just
same
different ways
object.
of
Yeah.
representing the same.
Yeah.
Okay,
You
so
you
what
take
does the
this.
sphere signify then?
I guess I
It's
think,
a particle. It's
Oh, the little thing.
Yeah.
Okay,
the
got
thing
it.
that is confusing for me there is the color. Like, is the color saying anything, or is it just?
The color says that this is the center of mass of these which have colors.
Fair enough. Fair enough.
Oh, so that's
Center of mass. And I mean, if you have an object, how do you summarize it in physics? 101. You take the center of mass and the average velocity. This summarizes.
I just noticed that the
and cumulative mass. Yeah.
yeah, I just saw that it's hard to see, but the root on top is the same sphere.
Yeah.
It's like
Yeah, this
it's
is
like
the
But the thing that is
yeah.
confusing me is the color, because I'm waiting for the color to mean something, because it means something.
The color just the color doesn't mean a lot, but it says that this is made of is the center of mass of this average velocity.
So I think just how you structure the object. It's like a hierarchical one, right? So all the leaves are connected, right? And then they're assumed to be a center of the mass. So you're in the lowest level, in the highest granularity, you just calculate the center of mass of all these levels. And then you go one level up, and you calculate just the center of mass of all these levels. And then the root is basically the whole object.
It's just the only thing that is confusing is the color there. Otherwise, yeah, like there are a bunch of data points, x delta m, and they have interactions on IJ, and you're just doing clustering on this, right?
Clustering.
Hierarchical, and then you just group them together.
So K means clustering. This is the regularity thing. Yes.
So we're assuming that all particles have the same volume, right?
Yeah. They have different masses.
Yeah.
It's important. But it took a process.
I mean, the one
But the volume is
they
not.
all have the same volume. As you break down, it's like 1/8 of the original one. Okay, so thanks. That's all. Thanks.
Okay, so yeah, so I mean these particles have interactions. The interactions here they assume a scalar interaction. Okay, so Rij is a scalar, so it's the stiffness. It's a Learned parameter, as we'll see it. Okay, so when you take a cluster like this and summarize it, take its center of mass and its average velocity, its interaction with the other clusters will be through this center of mass and average velocity. You will not have connections between these two clusters, direct connections. Your connections will be directly between these, the center of mass. And this, by this, you reduce the computation. Yeah, I think this is done. Okay, so the prediction, the algorithm goes as follows. You have this GH, which is this hierarchy of graphs. Each node in this graph has, as we said, position, mass, and position, velocity, and mass. Okay. Over time, you'll have a bunch of these with different states, different positions, different masses, different average velocities. So GH is the graph with the relations, and it varies with time. The states will vary with time. You start feeding these into the following neural networks. So phi f will calculate external forces. So in addition, you have external forces you specify in your environment. So the effect of the external forces, the effects is some intermediate representation of these ones. Phi c is the collisions. So whenever two objects or two particles from different objects become close to each other, then you'll have some interaction between these two objects through these particles, and then this term comes into action. It depends on some threshold distance. Phi h is the time factor. This part I didn't actually understand very well. So I just said it's how the object behaved over time. You're taking this into consideration. Yeah. You add these together, and then you feed them. So now we have the external effects between objects with external forces and so on. You feed them into you propagate these effects between the particles, because the particles inside the object. I mean, if you have a deformable object like a pillow or something, if you punch it from one side, it will this effect from the surface will propagate to the rest of the object, and so this eta will calculate this. I'll talk about it in a minute. So it will get also an effect, and then this effect you feed it into another neural network. So fully connected networks, fully connected layers, and give you a prediction. So PT, I don't know if I said P. Yeah, P, I, P, T. These things are the positions, velocity of all particles. So P capital is everything. All particles, positions, masses, or all nodes.
So from P you can calculate the next G, right?
Yeah, P gives you the state.
Right.
So you have your G. Unless you're still learning your R, the interaction, because R is learnable.
Oh, okay.
The interactions between the particles, you learn it in the training phase.
Is there anything else learnable, or just
The R.
So like none of the external forces are
No, you specify the external forces in your environment.
So the question, G is just P plus all the intermediate nodes of the tree, or like what is inside of G? Is it just the P vector, like with individual points?
G without the H is just the particles without the graph, this hierarchy. GH is the graph with the hierarchy and the state of each node. The state is the position, velocity, and mass of each node.
So G doesn't have any labels on its nodes?
Each node has position, velocity, and mass. GH. So it's a graph with the edges, nodes. The nodes have position, velocity, and mass, and the edges are the interaction, Rij. Interaction between any two particles.
Oh, so that's the interaction. It's not the clustering graph. That's like the interaction graph, like
It's this.
Yeah.
So this each node has position, velocity, and mass. This is center velocity, and the connections are the Rij. So
The
maybe I should
connections
have
are
to.
like within the levels because they're like adjacent.
No, also these connections, there is interaction between each leaf and each node.
children?
Yeah.
How so? Because doesn't the child, like, doesn't the parent, like, represent the folded in, like, set of particles? You know what I mean? Like, you kind of fold, like, 10 particles into, like, one center of mass. Do they actually, like, interact with, like, a, spring, like, constraint? Like, you know what I mean?
I mean, when these move, you expect this center of mass. You don't specify, you don't calculate it. You assume, through the interaction, you change it.
So my question is, if you do it that way, doesn't it make it unstable? Because some center of mass might actually kind of start oscillating through, like, solely through energy of its own, like, child particles, and it might actually kind of give you like perpetual motion. That's my kind of, you know what I mean? Like, if you instead of like doing it within levels where like particles interact with the adjacent particles, when you're creating like a circle because that parent gets its position and momentum from its children, and then the children can actually interact with it. And aren't you creating basically like a positive feedback, if you will?
So the interactions between these particles will happen through this, and you need to change the position and velocity of this from this. Then you have the interaction, and then you go back to get the effect on these particles. So it will have. I'll show you in one slide. It will how this propagation happens. Then maybe I don't know if this will answer your question or not.
But Rij between the smaller pink circles completely defines the position of the bigger big circle, right? Like you don't need separate interactions between the parent and the child, right?
I mean, calculating the center of mass directly.
Yeah.
But they don't do it this way. I don't know why. They use it. They use the effects. So the leaves will affect the parent and change its position, velocity, and so on. And so, yeah, to the best of my understanding. But yeah, I don't know.
So then, what is the relationship between P and G?
P and G.
So the next
slide.
So you end with P, right? And supposedly you use this P.
Yeah, P here will give you for each node the position, velocity, the mass is already there, but it will change the position, right? The prediction. What's the prediction? The prediction is that you have particles and you want to know what happened. The next time step, where did they move and what are their velocities? And this P will give you this information. So P capital is just aggregate of all these P's.
Right, I understand that. But the thing is that I assume the way you use, if you go to the next slide, the way you would use this is that then you grab that P and plug it into this pipeline again and calculate. If you want to build like the dynamics of the particles, right?
Yeah. Then you get a new G at t+1, and you add it to this. Yeah, so this is G at t minus t+1 till t. So the states over time. And this, now you get the new state, and you put it on the graph, and you feed it in again to predict at t+2.
So G is like part of a transition, right? From t-1 to...
G is the history of the states.
Yeah.
No, is it? Yeah.
GH is the graph and the state. So the graph with the state of each node.
But the P is only for individual points. It's not for the higher level like centers of mass. Because those are like
P
deterministic
is
functions.
for, I think P is for everything.
Everything.
Unless if someone read the paper and disagrees, please tell me. But what I understood is for everything, because there are interactions. It doesn't say, well, go and calculate the center of mass and so on. Only initially you calculate the center of mass, but then for the clustering thing. But then you just leave it for the network to
So the interactions are not mediated through like Newtonian, like just summation of like superimposing over things. It's just another like stiffness, another like strength.
It's like blur. It's not clear-cut physics. No, there isn't any clear-cut. Only in the initialization. At least there is an algorithm in the appendix which says how do you do the clustering and so build the graph. But to the best of my knowledge, they don't use it later on. They just now go on and feed in. These are the new states of each node for all the nodes, to the best of my understanding, and then you feed it back.
Yeah. So in the paper it says P plus the relations form G.
Yeah, the RIJs, so these relations.
Yeah.
The interaction between the nodes. So the nodes and their interaction.
So what is
So the labels of the nodes and the labels of the edges.
So what is the time dimension then on G?
I mean, so the state evolves with time, and you
But
take.
that's an interval, right? That's T minus
Oh,
T.
so they take either one step backwards or two steps backwards in their experiments.
So capital T is just a time step?
Yeah, so capital T can assume it's 1. So so you take the states at T minus 1 at T, and then you predict at T plus 1.
So capital T probably is a constant,
Constant,
and T
yeah.
plus 1 is your prediction, right? You look at what happened from, I don't know, a few time steps before up to T for G, and you predict Pt plus 1. So you observe up until T, and then you predict T plus 1.
But the thing is that in the previous slide, there was no mention of time, right? In order to build this tree.
This is the initial thing, yeah.
Right, so in order to build this, you're only using PIs and RIJs. There's no mention of time.
Yes.
So how
this
is
is the
time
initial,
added then?
the initial step.
You
Okay.
use that H parameter of history.
Sorry?
There's the H parameter of history on the next slide.
Okay.
Phi H. That is that for the
Phi H
time?
is for the history, yeah. So it extracts history information. I didn't understand it very well, but it extracts history. I don't know why you want to extract history.
So I
But
guess
does that
Because
mean
you already have velocity, you have forces, then you should be able to predict the future. But maybe the history is because they do some experiments where they don't know the properties. So Rij is not specified. Maybe the history helps you to learn the Rij on the fly, like as not in training, just in the test. I don't know. So this phi h, I didn't understand why they need it.
so you have velocity of the previous time step, right?
Each part, yeah, velocity and position, and then you have forces. You should be able to figure out what will happen next. But I don't know why they have this phi h.
What does the data set look like exactly? What's the input and output?
Huh?
What does the data set look like?
So the data set is a bunch of objects, points, made of points, and on the surface, and they interact. Like you put some external forces like gravity,
Right, okay.
and it falls, for example, on the surface bounces.
These points only have like position information, nothing else.
Position, velocity, and mass.
Oh, okay.
Particles, position, velocity, and mass.
So just to address Amir's point, if I'm not mistaken, I think the previous slide is just the initialization, and then evolves over time.
So what I don't understand is that I don't think that capital T is 1, because otherwise they would have just said T minus 1,
Yeah.
right? So it is probably...
No, in their
It's the
experiments.
dimension of your
This
system.
is general, but
So
in
it's
their
order of the system, or of the integrator. So if you,
Right,
if you have
exactly.
a third order, like you have like the last 3 time steps, and the reason you have so many phi's kind of stacked is because you're kind of uniformly applying all those phi networks to each previous time step. I think that's my read of the diagram, but
So that's exactly what I'm saying.
Yeah.
So G, is G, for example, the 3 graphs corresponding the last 3 steps
3 times
that you'd somehow do something on them with phi of h, which would be just add them up, which is like, I guess, like integration or whatever.
Yeah. And the feed forward is kind of uniform because you're applying the same network kind of each time step.
I'm not sure about applying
Yeah.
the same network on each time step. Yeah, just I'm thinking. I don't know, unless you know. But maybe you're right. Maybe you're right. Applying it.
I guess if you move on, we might understand what's happening.
Okay. Did we cover this? Yeah. Any questions? Okay, so so the external forces, the collisions, as we said, these summarize these collisions and external forces. You add the effects. Now you feed them into the object to see how the object itself is deforming or changing. Okay, and this is how they do it. So it's not exact physics also. So it's effects. Don't know what's effects. Some vector. So you have a sender particle, receiver particle. Divide them into sender, receiver, according to the direction of the interaction. So these RIJs are directional, not necessarily bidirectional. So one particle affects the other, maybe not in the opposite, especially in the tree. Like the leaves will affect every particle, the parent and the ancestors, but not necessarily in the opposite direction. Okay, so sender receiver, the particles. Yeah, so you have, this is the graph, okay? You have the leaves, the original set of particles, and you have these centers of masses and so on. So the leaf affects in the first step in this algorithm. The leaves are the senders, and the ancestors, these, okay, are the receivers. So the senders affects the receivers. Affects them means there is some function that you put in these two things. One is the sender, one receiver, and it gives you out the effect on the receiver. So the sender affects the receiver. Sender affects the receiver. Like a force on the receiver, something. But it's an effect. Okay? And then in the next step, the ancestors here are these things affect each other on each level. Sorry, not the ancestors. Each level, the particles which are connected affect each other. So also senders and receivers, but now it's bidirectional. So okay, so each particle is a sender and a receiver at the same time. This is the second step. So this WS. Okay, siblings affect each other. Okay, I mean if one particle moves, the others should be affected. The last step is going downwards from the ancestors to the leaves. So the ancestors affect the leaves. So, the ancestors affect the descendants, not necessarily only the leaves, also maybe the intermediate ones and the descendants, according to the connections.
So the L2A part is kind of like that as well. So you
L2A?
Yeah, like the first step.
L2A from the leaves to the intermediate nodes. The parent and to the it's connected to all these. So to the parents and to the ancestors. Okay. I mean, if these move, you expect at least the parent. You expect the parent should be updated, right? Because it's intuitively it's the center of mass.
So the only question that I have, because if the effect is across like many generations of a tree, and those 5 functions, they are like, they have the same parameters, they share parameters. You don't care like which ancestor, which descendant you're talking. Like it's just the same function, like the same learned parameters kind of govern all of these functions. So
the relation.
Yeah. So the Phis are not dependent on the identity of PL, PA, for example. It's just the same phi. You only like
here?
the
You're talking here?
momentums and like
No, I mean if you have a different position,
Yeah.
then you have a different effect.
But the functional form is the same. Like one set of parameters.
The functional
are trained
form
for
is
that.
a neural network. I mean, once you train it, it's the same. Yeah. Then you use it for prediction.
So the weights are kind of tied. So you don't care. Like you're not learning a separate function for like.
No.
A and B. And
No, it's
another for
the
like
function
C.
is fixed. These change. Yeah.
Okay.
During training, you learn this function.
The
It's a
parameters.
neural network. The parameters.
So is it plausible? Because how do you do that? Because like the effect of like a third level descendant should be much less kind of pronounced on the parent, like as opposed to like immediate ancestor descendants. If you're learning the same function, how do you discriminate against like like just a small?
Sorry. Yeah. I mean, you feed. Okay, I understand also. In the neural network, few slides, you feed in everything. You don't feed them separately.
So you leave it up to the.
As I understood, you feed all the positions, all the ancestors, and you spit out all the effects.
It makes it kind of makes sense because like when you're aggregating too much, probably like the deviations are going to be higher. So like your function could be more or less kind of sensitive if they're close by. If they're already close by, maybe the effects like the momentums and positions are close by. So you're not feeding in. Are the P's like the entire like state vector? Like is it
P and PA here.
Is
So
position
here
velocity?
you're summing. So I think it's the individual particles here.
but like all of their degrees of freedom? So their position, their velocity, their acceleration.
You feed in everything. You need the mass, velocity, and position, and the forces to figure out what will happen next. Okay, well, maybe later on you can also.
No, like
next.
I'm definitely
You're good.
I'm good, yeah.
Okay, these are just some equations, like equations. Yeah, so you feed in the original effects, then you get this EL to A, you feed it to get the WS, so the siblings affecting each other. So it's a sequence of events. These are the neural networks. So here, so you feed in the state. This is the phi h of each individual particle. So no relations here. Also, you feed the states of pairwise particles, sender receivers, and the interaction. So this is for the collision. And here for the external forces. So you need the external force on each particle. And you feed it into fully connected network, several layers, and then you get effects, effect. Intermediate representation of the effect. You sum them up, you get the effect of collisions, external forces, and the history.
I have a question. So the second term, like the collision term, because normally if like two particles belong to the same object, rigid or non-rigid, you probably have a non-zero like Rij, so because there's some attachment, whereas like kind of by definition collision is when things come in physical proximity, but they don't have any kind of strings attached, like strings attached to them.
So this happens dynamically.
So that
objects
coefficient is just dynamically determined, or
no, the Rij. So you make links between objects as they become as this. Like if you have a box and a box colliding,
So
they interact. At some point they come close to each other, some threshold distance. There's interaction. You put these links. Exactly how I don't know, but you put these are these happen dynamically. So RRJC, so collision. So they happen dynamically.
So you have to do like collision detection out of that. Like it's
Yeah, there is the distance function which sees which parties are close to each other. Okay, here's some other effects. These are the external effects and history, collision. And then you feed this into the next network, which is the propagation of the effects into within the object. So internally, we talked about this here. This propagation, leaf to ancestor to descendant. Okay. So this is leaf to ancestor.
So you're not sharing. If you go back, oh here actually. So you're not here. So you're not actually sharing the parameters. So at each.
So these are the weights are shared.
Oh, between I see.
All this. So if you, but there's a sequence of events in the prediction.
Sure.
So this is what. So you feed in the positions, relations, and external collision effects history into the network, and the sender receiver. So this relation summarizes sender receiver. RLA is different than RAL. RLA means L is sender, A is receiver. So
Sure.
direction. You get the effect. You feed it back into the next thing. This is the between siblings. You get another effect. You feed both effects. And you get the effect from the ancestors to descendants. I mean, at the end, you have the leaves. The important thing is the leaves, right? You want the leaves to affect each other. To reduce the computational burden, you do all this gymnastics, okay? But the leaves will affect the ancestors will affect the leaves. So you need to go back to the leaves. You take all these effects, you get a new effect, sum them. Now we feed this into a network to make the prediction. So you have the effect on the particles. Now you want to know what happens. Predict what is the position and velocity. So this is the prediction. Okay, so the loss function for training. After that, we have some examples. The results. So the loss function, you want to figure out this stiffness, okay? The property of the material, the stiffness, how strong is the bond between any two particles, how they affect. So the parameters, you learn them, and you have the loss function, which is, so the deltas, this is at each level. It's a local, the delta IL, as I understood, is the local coordinate. So you have the node at the top is the center of mass of the whole object. Then you have centers of masses of the, yeah, you understand. So you have centers. So this is, as I understood, the local coordinate at some level in the graph. This is the global coordinate, okay? The coordinate within the environment. This is the pairwise distances, okay? And you want the prediction to match the actual ground truth. So you do a simulation, which you assume is a ground truth, and you want your prediction to match it.
Sorry, what was the difference of the first term and the second term?
As I understood, you take at each level local coordinates, and here you take the global coordinate.
So the first
And this tells you what. So the global coordinate is your local coordinate plus the coordinates of your ancestors. So at the centers of masses of your ancestors, you get your global coordinate.
So the first one is deviation.
Deviation from the center of mass. You can assume.
And the second one is the absolute.
Absolute coordinates. Yeah, good.
The thing is, if your frame of reference is centered in the parent, so isn't your delta I at t plus 1? And so the delta I hat, isn't it the same as you know what I mean? If you're adding the coordinates, or if you're subtracting the coordinates of the center point of the parent as the frame of reference, it's not going to make a difference. If you're calculating your data in the transformed coordinate frame, it shouldn't be any different. So I don't get that part.
This is if it's the center of mass. If it's the actual center of mass. But
No,
we're not doing it. We're assuming it's the center of mass. It's not necessarily may deviate from this.
No, I'm not even I'm not even talking if it's inertial or if it's not inertial, like a coordinate system. Or if you're subtracting something from both sides of that equation, it doesn't really make a difference. I'm not talking about
so
the
these
real center of mass.
Okay, so these are, I think, they're normalized for each level. They want because some levels have tiny deviations, movements, and other levels have large motions. Yeah, I mean, it's also confusing for me. But the best explanation I have is that they normalize at each level, so maybe this makes the difference.
The reason I'm asking is because the parents are they're not real objects. They're assumed objects, the higher levels of the tree.
Yeah.
So whatever you do, so you don't have any ground truth label at t plus 1 that you observe, and then you kind of calculate the loss, the delta. So even local deviations, because both sides of that subtraction are in reference to a certain thing that is not even observable. Mm-hmm. So you're adding one quantity to both sides of that minus sign, so it doesn't really make sense.
I'm not
you know
sure.
what I mean? Yeah.
I'm not sure. Yeah,
You score it?
Yeah, because you see that one, the L is at the lower levels, and let's say there's 8 particles and 64 particles at the bottom.
Yeah.
And those 64, once you subtract truth, so let's say there are 2 nodes, right? The truth and the predicted, there are 8 of them. Once you subtract and square them, and the ones at the top, once subtract and square them, the value is going to be a bit different because of the squaring. If there was no squaring, then yeah, that would be the same. And also you can weight them.
So this is basically each of those loss terms are how off the mark I am, in step t plus 1, what is the realized value and what is the predicted value.
Yeah.
So how much off the mark I am doesn't depend on the frame of reference. So if I add a fixed, you know what I mean? So the local frames of reference don't the IL ones don't make any sense to me. Because it should be the same quantity. You're adding the same thing to both of them. If I moved by or if I was off by 2 centimeters, doesn't make a difference if I'm off by 2 centimeters relative to the same center or to some other center. You know what I mean? The difference vector is going to be the same regardless.
Let's say we have 2 particles, right? At the parent, and then we have 16 particles at the first layer, right?
Mm-hmm.
And we have predictions for each, and we have the truth value for each.
Yeah.
So the first one is, let's say, 1 minus 2 squared.
Yeah.
But the lower ones, the same one that we defined earlier, which is the center.
You don't observe the
parents,
parents,
right?
Yeah. the parents don't exist physically. That's the thing. So best we can do, we can sum up from the children up. So you know what?
I mean, I think in the ground truth is the center of mass. They calculate it as center of mass. I'm not sure about
But the difference is what he's saying. Essentially, it is subtracting before squaring or after. Right? That still makes a difference. Like if you calculate the parent and then calculate the difference and then a square, it's a different quantity versus squaring first and then adding them up.
Intuitively, I don't really understand why, but this mathematically, there's should be
You're saying
something.
the parents are not observable?
Yeah, because the parents are like, you know, they're not physical things. It's just like I fold in like these 4 particles into like one level up. It's a cluster. It's kind of an artifact of the of how you pose
You
the
calculate
problem.
them.
Yeah.
The parents, you calculate them, or you
So you calculate the quantity, so you don't observe the ground truth.
I guess we just see
No,
how
no.
you calculate the parents. Like
The-
do
the-
the average. If it's just an average, then the squaring would make a difference. If
the
we
ground
calculate
truth
the
should be the
parents-
center of mass.
So, yeah.
I'm not sure if I
Apparently
read
the
it,
center
but
mass
I
is
assume it
still-
should be. You should be able to calculate it as center
Yeah,
of mass.
you just run
ground
k
truth.
and then for this data set it's deterministic. If you set a k, and then you should be able to determine the hierarchy, right? Just by calculating.
Yeah, I mean, for the ground truth, I think you can calculate set of masses and so on. But
Oh,
for the
okay,
the prediction, it's done through the neural network, as I understood.
Yeah, and ideally, it's predicting what the center of mass would be. So, like, I think, well, for any center of mass, you can have a range of different distributions of its children, right? So, like, if your ground truth is the center of mass of distribution of particles, then those particles can be in any sort of state.
Yeah. So maybe the spreading of the particles here takes into account.
So the intuition behind it is
Maybe this is the intuition.
The reason you want to do local is because there could be like this, like say 16 particles like deviated collectively, like on a larger scale, but still locally, the loss is small, but they deviate together. They all have by some offset probably, so that's why you need both the local and global. Could that be one case?
The explanation here.
I think there are 2 things that we're trying to capture. One is the relative motion of particles with respect to each other, right? We're capturing that with the first term, I think. But there is also a global motion of all particles together, which is the motion of the center of mass, which you're capturing with the second. And now that I said that, I don't know what the third one is now.
The third one is the distances between any 2 particles.
Which is
It's not the motion, it's the distance.
Yeah.
So you want the
Oh, that's the
distance to be
distance, okay.
preserved.
Right.
You don't want the object to change.
Sure.
I mean, if it's a solid object, if it's a cube, you want it to stay as a cube.
That's right.
So this helps you to preserve the shape. Although in the experiments, it doesn't do that well.
And for some reason, the first term and the third term have related coefficients. Like that's alpha, that's 1 minus alpha.
Yeah, the coefficients are complementary.
The first 2 terms are multiplied by alpha.
I mean,
That's
the second one there is still beta, but the first term is literally times alpha, and the third term is 1 minus alpha. So I assume somehow they weight each other out or out.
Does that matter?
I don't know. That might be just
Just you want 2 different coefficients, you can. Does it matter if you make it?
Oh, yeah, okay.
this
Oh,
one?
sure.
But the thing is that if the first term, like if alpha is closer to 1, it means that the first term is more dominant than the third term.
Oh yeah, alpha you learn it. Or, yeah.
Yeah, I agree with him because like usually when people use more than one coefficient, and this is a 2-term formula, having more than one coefficient doesn't really make sense. You can just change. It's just equivalent as.
You want the importance. What's more important? One parameter is enough to.
So like, but you can achieve the same with just one coefficient.
Yeah. If you give both 1, it's basically alpha is 0.5.
Yeah.
Quick note. I think I got the first part. So for the parent level, it's possible that the error is 0. So two parent particles are exact same location, but the children are like one sparse, and the actual one is like 30.
Yeah, you could have the same center mass, but be wrong about the individual particles. Look at it out.
So that first part will kind of tell you if the children are all.
Yeah, I believe we think that's just
I mean, you can have the same set of mass. The particles, from what I heard, particles spread out or collected into the same cone. So one is telling you about the general behavior, and one is telling you about the details of the particles.
I just don't get where the delta ILs are coming from, because they were not like defined before.
The notation, sometimes I get confused also. But I assume the delta IL is the delta we talked about before, which is the delta is a change in position. You can say that the velocity is the delta, is the velocity per unit time step. I assume. I mean,
maybe they started just offsetting like the TC term, so to speak. So yeah, they started by talking in the difference domain, and then and everything is like, you know, this is I think so, because V would be like velocity if they were not like talking about delta. So
I mean, the velocity is. How would you calculate the velocity in 1 second? You just take the difference in position.
You're kind of like your object has a frame of reference. Like your entire like scene has a frame of reference. So you can have velocities, you can have absolute velocities, but then if you kind of if you subtract the delta or the initial values, if you will. I don't know. I can't pretend to understand this until
I didn't write the paper.
Let's see examples.
Yeah. I think, yeah, I'll show some examples. We'll go back if you want. So yeah, this is the training and the testing quickly. So for the ground, so they use this flex physics engine, Unity 3D. I don't know much about these things, but it's realistic physics engine, particles. Takes meshes, change them. You can take a particle representation from a 3D object mesh. I think they do this, or is it included in the package? I'm not sure. They do some scene objects with some random forces. They put some details in the paper, colliding with gravity, without gravity, going down on the surface, bumping on the surface. The shapes I showed before, I'll show it again. Yeah, so the training is done on some objects. You learn the stiffness, Rij, and then you use it in the same instance in the testing. So they do it on rigid bodies, complex shape, deformable bodies. They have a lot of tests, and they're not all good results, but I'll go quickly over them. These are, again, the objects colliding or bumping into surfaces. These are the surfaces. They don't move, they're just static, infinite mass. Some results. I don't have a lot of comments on these results. There's some quantitative results in the last slide. These results, you have some sphere falling out of a bowl. You can judge if it's good or not good. I mean, this is the images are really tiny also, so you can't see much of a difference. You can see differences actually, even though they're tiny. But they say they predict the general trajectory and they give you a general statement, predict general trajectory, and it's realistic. I mean, for an observer, it seems realistic. I don't know what's this. I mean,
Is it how much time they have?
first, initially, I forgot exactly how many. Yeah. But you can see the differences start from the beginning.
The second one, their object is exploding.
Can I move you? Second one?
Like
This
the ball,
one?
disappears. Like
yeah, the ball falling into the ball.
The green ball is just
Yeah,
like not
it's just-
doing-
It's getting smaller.
it just vanishes.
But it also turns into bunches.
Maybe there's a distance.
That one's supposed to be 5 balls falling into a ball, I think.
Yeah, fine.
They start out as a cluster, but it's like originally 5.
They're like separate, so like they're not attached.
Yeah.
Okay. I see. So like, cool.
And then there's 5 balls, right? But how? Yeah. Anyway, this is a solid, rigid pyramid falling on the floor. Also, I don't know. I think this is a nice one compared to the next slide. Bumping of a surface, 2 objects colliding, one heavier than the other.
So,
Uh,
so the first one on top, it hit the ground and just stuck.
yeah.
Yeah.
It's like,
This one's
bad.
Yeah.
This is the predicted. This is
Yeah.
the ground truth. Yeah, I didn't like these results. So, cylinder colliding with the pyramid. Yeah. The problem is it's really tiny. Obviously, but I think it's a difficult problem. So.
With a rigid sphere, I don't know that having like a particle level model really adds much to it anyway.
You need elasticity. I mean, include elasticity somehow.
Oh, it's truly rigid.
So this is deprived of elasticity. It's just got stuck on the ground.
So yeah, how do you like make the judgment like when a collision happens? How do you make the judgment call of like do you like get the RAJs
Threshold
out of thin
distance.
air? No, like distance threshold. But once you determine that something's colliding with something else, do you actually kind of like declare by fiat that this is going to be the RAJ, this is going to be the stiffness of this ring force? That kind of you know what I mean? Because that will determine literally what the
The
material.
RIJs, when you have the collision, I don't know how maybe this is why you need the history. I don't know how they calculate the RIJC because this is happening during the testing. Or maybe from previous collision experience. It's like one line. They'll publish their code later on, I think.
Yeah.
But they didn't specify exactly what's going on here.
So another question, I'm just curious. I probably didn't look at the paper myself, just to see if they give any kind of any reference to this. So there's like a bunch of things there's a bunch of studies by psychologists way back in the 80s about like naive physics, like how people's perception of how objects behave differs from the actual Newtonian physics. And apparently there's yeah.
Did you see this paper?
Yeah, if you're swinging like a ball, people think that it's going to go on like a
Curve.
like trajectory, or like
If you swing a ball and leave it, people will think it.
Yeah. So
it makes sense.
it does make there's very like reliable deviations of how people kind of conceptualize physics versus like how physics works.
Yeah.
Have they did they replicate this? Because this is
they assume that we're good predictors. We have good sense.
The data that is coming from a physics simulator, so I
Oh.
assume it is based on reality rather than drawing perceptions.
This was a good. Yeah, it's physics.
it's
simulation.
actual the
The
ground
ground
truth is
truth,
actual
physics,
Yeah.
not what people think. Yeah. But maybe this is why it's not giving very good results, because people don't give. They have realistic conception of what will happen, but they don't know exactly. Okay. This is the duck and the bear. Complex deformable shape experiments. I mean, this is
It's pretty good.
I'll leave it to you. So, but they have some they have some problems. So they talk about problems. Which is, so here, this is the predicted, and it separates into breaks. Here it breaks also. Here it's bumping over steps. I don't know if there was a problem, but it's okay, I think, relative to others. This is going over complex surfaces. This is going over a slope, several objects. Stack of boxes, and they collapse from the very beginning. This is part deformable, part solid, and it's I think they get what they expect here. Anyway,
The second row is interesting though. Like it doesn't, like the stacking doesn't work, but the falling kind of works.
like in general, how it's falling.
Yeah.
But compared to the other, it's not. Yeah, I mean, they say it makes sense, but it's not the right result.
Yeah.
Okay, so this is more of a result. So stiffness, you expect as you increase the stiffness that the deformation will decrease. So which is what happens. And there you expect as the masses increase that the displacement will decrease from the collision. Gravity effect also, objects fall faster. This is what they said, which is right, but this is the comparison with different variations. So this is multilinear perceptron. So you give it the coordinates, the forces, and spits out the directly without all this complex structure, the prediction. The MLP, fully connected graph. Everything is connected to everything. Some other variations. Instead of having neural network for the force, like getting the effect, they just feed it the forces, they feed them directly into the next step. The same here. No history. You remove the history. The loss function, so they play with the loss function. So no distance preservation, or no local loss, or no, sorry, here is only local loss, I think, and here you have global local loss. So this is everything. And they compare and they get better results on their error measures. Yeah, I think this is it. Thank you.
Awesome.